Okay, so I like to start with my moon because I like it so much. So the problem, I've said this problem like 8 times, but really this is the 5th time. So the problem is, here's an object that's moving towards the moon, and it starts 3r and ends up with 2r, so how fast it's going, starts from rest. Boom, okay. So the last time I did this problem, what I did was use the work energy principle. And and I left it up here, this is the same thing. Since I have a non-constant force, the gravitational force increases as it gets closer to the moon, then I had to integrate. So I integrated to find the work done. Okay, now it turns out that with gravity, the path of integration doesn't matter, only the limits of integration. So if I went from, I'm deleting it because I'm getting points up here, from here to there in a straight line, and then I went from here in a circle around there, I would actually get the same thing, and I should show you that. I'll do that at one point. Oh man, that's going to be a lot of calculations. I really want to do that though. Okay, so since it only depends on the points, the endpoints, then I can make that work a potential energy. What I can do is to take my work energy equation, I should start erasing stuff. So here I have this. Work equals the change in kinetic energy. That's what I had. And I calculated this work. Well, if the work doesn't depend on the path anyway, I can just move it to the side. So I get 0 equals delta K minus the work. And then I call this change in potential energy the work, the negative work. So that means that my change in potential energy is essentially the same integral. So and I'm not going to derive it because I already integrated this once, right? And I didn't make a mistake, but I could have. So I don't want to make another mistake. So that means that if I declare, let's just redo this whole problem. So if I declare my system of the ball plus the moon, I have to include the moon in the system, then that gravitational force is an internal force and it doesn't do any work on the system. So my work is 0. And that's going to be the change in kinetic energy plus the change in gravitational potential energy. So here's an important point. You can do the ball as a system and do work done by the gravitational force. Or you can have the ball and the moon in the system and do no work done, but have a change in gravitational potential energy. You can't do it both ways. Okay? If you do it both ways, bad things happen. So in this case, I'm going to say the kinetic energy is 1/2 mv squared. The potential energy, U, is negative g, mass of the moon, mass of the object, over r. Now, this negative is indeed important. And in fact, this is a change in kinetic energy and a change in potential. The potential actually isn't perfectly defined. This is actually a cheat. This says this is the change in potential energy with respect to infinity. This says that at an infinite distance away, there's no potential energy. And as you get them further and further apart, the potential energy increases. And that's why there's a negative sign here. Okay? Because if I plotted this potential as a function of r, it looks like this. So this is both increasing and getting closer to 0. So that's my potential. But it's the change in potential energy that's important. Okay, let's put this all together and do the problem. So now I have 0. So I have 2 points. I have point 1 and point 2. So 0 is the change in kinetic energy, K2 minus K1 plus U2 minus U1. And I want to solve for K2 because I want to find out how fast it's going. This is a really great problem. I'm going to leave V1 in the problem, even though we're going to set it equal to 0. So let's just put in our values. So I have 0 equals 1/2 mv2 squared minus 1/2 mv1 squared plus the negative potential 2. So it's going to be minus g mass of the moon m over that 2. It was at 2r, right? That's how far away it was. And then at 1 it's at 3r. Minus a negative, so it's going to be plus g mass of the moon mass over 3r. So you'll notice that this is going to be bigger. Yeah, so I'm going to add these to the side to solve for the final velocity. And so this is bigger, so that's good. It's going to come positive. So if I solve this so the masses cancel, and if I solve this for V2, multiply everything, add that stuff to the other side, multiply by 2, I get V2. And I'm skipping a step because is the square root of V1 squared. Yep. Plus G M M over 2R minus G M M over 3R. Okay, so if I put in V1 as 0, I should get the exact same answer as what I got before, because the math is the same when I integrate it, because this is the same as integration, so I'm not going to do that. But what I will do is show you something even cooler. Okay, now what if I want to spice up the problem? Okay, so here is my moon. I'm going to start with it having some initial velocity. Let's say I'm going to pick 500 meters per second. So it starts up here at 500 meters per second, and it goes down to here. Now it starts at 500 meters per second, and it's going sideways, and it goes right there. Which way is it going faster? And the answer is, it doesn't matter, right? Because according to this is the magnitude of the velocity. It doesn't matter where it ends up. It all depends on the final positions. And those have the same final R position that have the same final potential energy and the same change in energy. So here's the situation. Here's point 1. Here's point 2. And then the other way is like this. Actually, let's just say it ends up over here, because I don't actually know where it ends up. Those two will have the same speed, different directions, same speed, due to the work energy principle. I was going to do another problem. I can't remember what it is. But definitely, if you can do, in a case like this, the work potential energy with potential energy is your best bet, because you don't have to integrate. The integration is already done by using this as the potential energy. So I'm gonna do a numerical calculation on another video, because what the heck, right? It's got to keep making videos. These two paths, and show that they're the same thing, and probably with the energy graph too. Okay, but that's it for this one. Wasn't too bad.